Okay, so if we win, great. Else, that number we rolled becomes our new target. Okay, so while our game over is equal to false, we roll the dice, we calculate the totals of some of the dice. If we get our target, great, we've won. So if total is equal to target, print, you win. Set win to true. Set game over to true. I'm not sure if this flag is necessary. We might go back and delete it later. And what is a flag? A flag is a variable that just is set to either true or false to indicate that something has happened or that something has not happened yet. Okay, if it's not equal to the total, then we need to see if it's equal to 7 or 11. So else if the total is equal to 7 or the total is equal to 11, in this case, we print you lose. We set win to false. And we set game over equal to true. And now we're at the bottom of the while. So now we're done. Print done. Or game over or something like that. There we go. That's pseudocode. That's not programming code. It looks kind of like programming code, but it's not really. So the goal of it is to, you roll 2 dice. If you get a 7-11, boom, you win instantly. If not, that becomes your new target, whatever you rolled. Then you start rolling again, trying to match that target. If you get that target before you get another 7 or 11, you win. If you roll a 7 or 11, which would have made you win up here, you lose. I didn't invent the rules. I think that's pretty close to the rules for the game. And there are some real vagaries here. We don't show how to roll the dice, you know. We don't show using a random function or something like that. So there's some stuff here that's being glossed over, and that's okay. That's the idea behind pseudocode. So I'd like for us to all flowchart this one. So go to lucidchart.com, log in. Hopefully you remember your password. So broadly, we're going to have the 2 sections. The first section is going to be the first roll, and then the next section is going to be the subsequent roll. So I may wind up drawing 2 stacks, you know, one where the line of the bottom one hooks up to the line of the top one. All right, they all need to start with a little shiny pillbox. And then we have these flags. I don't think we ever use this one. I don't think we ever set the win-loss flag. I mean, I don't think it actually matters. I'm going to delete all reference. No, I'm not. Who knows? We may want to do something cool with that someday. Alrighty. So, we have 3 little bits of math. I'm going to put them in one process block just because they are related. If you have several different statements of math, but they're not, you know, exactly related, like they're not just initializing variables, don't just put a whole bunch of math in one block. But in this case, I think it's okay. So we're going to set game over equal to true. Set our target equal to 0. If you need to go to the next line, you just hit Control Enter. And then lastly, set winner equal to false. So here we don't know how it works, but we need to roll the dice. This is kind of a function that we haven't mapped out yet. I think I will make it a function. A function is something that starts with that DEF keyword, and it's a block of code. I'm going to use this predefined process block. Anytime we call a function that we are going to write, rather than a function that comes built into Python, we want to use the math block, but it has the extra racing stripes down the side, the predefined process. So we're going to say total is equal to roll 2 dice. Now that does not look at all like programming code, does it? I'm going to add parentheses after it. And take the spaces out. There, that looks more like programming code. But I'm leaving it a mystery as to how that actually happens. What that roll 2 dice function looks like. In fact, let's just make it roll dice. That's easier to type. Now this is the first if check. Whenever you have a decision block, you have to have 2 lines coming out of it. This one's going to be if total is equal to 7 or total is equal to 11. If that's true, we want to set our game over flag to true. And we want to set that we won. And then we want to print out our message whether we won or we lost. It'd be nice if we actually printed what we rolled, though. Maybe that would be part of the roll dice function, but we should actually, between total roll dice and then our if statement, we should print out what our roll was. Let's do that. Print total. Just place that right there between those two. Now, since this isn't a while loop, we're not going to have a line looping back up to it. It is a if statement. It has 2 parts. It has some code that executes if it's true. It has some code that executes if it's not true. If it's not true, we want it to do something else. So here's where I'm going to put my no parentheses else code. This one sets our target equal to what we just rolled. I'm going to go put else in parentheses after the no else statement. That's not strictly necessary, but indicates, because people want to put the word else in a big decision block just because they're used to seeing a line-to-line correspondence between the flowchart and the code, but there's not. There's no else block. There's no else shape. So it's just a branch off the if statement. All right, then the end of the if statement, we'll make a circle. Have those 2 things hooked back up together. All right, that's pretty sloppy, but that's the logic for the first part of it. There's no print message here. We probably should have print. Yeah, here we printed what we won, or the total, but we didn't print a yes, no here. But we'll do that later. After the whole code is done, we'll print whether they won or lost based on the state of that win block. Maybe that's it. Now let's put one right here. We're going to put a print statement that says print you won on the first roll. Okay, there's our rather crudely drawn flowchart. Then I need to go back up, and we're going to do the second roll portion now. This was just the first roll. I'm going to see if I can add a text comment up here. Let's see if this will work. So I drag this brace, this curly brace, and I'm going to add a comment that says first roll. All right, now for the second batch. We need to keep rolling until we are done. However, if the game is already over, we don't want to keep rolling. So we're going to have an if block. While game over equals false. And now we want to roll our dice again. Total is equal to roll dice. And I could make that less specific. I could just word it as non-scientifically as we did when we were doing the flowchart, the pseudocode. And now we have different if logic. Here our logic is if we roll a 7 or 11 now, we lose, else we check to see if it's our target. And in the pseudocode, I did the target check first. That was the first check before we did the second, if total 7 or if total is equal to 11. So let's check that. If total equals target, if we've done some good stuff, we will set our flags. We set game over to true, and we set win to true. If that's not true, we're going to use an elif block, else if. So on the no side, elif or else if total equals 7 or total equals 11. And if that's true, we need to print that they lost. And I forgot to put a print message on this one. We'll leave that alone. set game over equal to true, but set win to loss, or set win equal to false. And if that's not true, we just go back up and we loop again. So let's draw a little circle underneath everything so that we can hook our stuff back up. And since this is if-else-if logic, we're going to make both of these little branches here just go directly to the end. Okay, so that's our second roll logic. Once we are done rolling, this hooks back up to the while loop, to the while statement. Okay, so while game over is equal to false. The game isn't over, so we roll our dice. If we roll our target, yay, we've won. We set game over equal to true, and we set win to true. Else, if the total is equal to 7 or total is equal to 11, we print. No, we don't print, but we set our flags game over equal to true, but we set our win to false. And then all of that's done. I really don't like the logic, the flow of the else-ifs, the way that I'm diagramming them here. I don't know. See, what I'm hemming and hawing over is that if these were just a series of if-elses, we would do them like that. But once you've done this one, you can't do that one. They're mutually exclusive. That's the point of using an else-if statement. So I'm going to leave it like that to try to indicate that these are two mutually exclusive statements. Meaning that if our total was equal to target, we do that one, but we cannot possibly do that one. And so I don't want a line hooking it back up to there to make it look like we can. Not digging that. Okay. And so now that once we are done, we just come down here underneath the while block, and we need an if statement to determine whether we're going to print we won or we lost. So our last if statement is going to be if win is equal to true, then print you won. Else we print sorry, try next time. Alright, I know it's kind of far away now. Here was the last block that we just added coming off the while block. After we've exited our while loop, if win is equal to true, we print you win, else we print you lost, try again. Now the only thing wrong with my chart now is that I have two separate chunks of code here, but this one doesn't hook back up to the other one. So I'm going to put a comment over here that says second roll and then I'm going to draw a line from that circle here up to the top of the while block. Alright, I'm not super happy with it. It's too small for everybody to read, but it is kind of a complicated flowchart, so I'm not really sure how much I could go towards making it more legible for everybody. Alrighty, I hope that I haven't made it impossible for y'all to follow along with. I could print this out if anybody needs a copy of it. Alright, let's actually turn this into a game we can play. Is everybody done with this part? Can we get rid of this on the screen? How you doing? You need a coffee? Okay, yeah. Quite reasonable if you ask me. Who else would like a copy? 1, 2, 3, 4. Wes? Anybody else? That's spare. Alright. Hopefully this part makes sense. Roll the dice. If it equals our magic numbers, great, we win. If not, that number becomes what we need to roll. Then we come back over here. And while the game is not over, while our flag is still set to false, we roll again. If it hits that target, great. Something good happens. Else, if the total is 7 or 11, something bad happens. If neither one of those things are true, then it, keeps looping over and over until the game over flag is set to true. It falls out of the while loop. And we print whether they won or they lost. Go ahead and open up idle. Let's put our name up at the top. Name or initials. Dice program. The date. So this is the first roll section. And then later on we'll have our subsequent roll section. I should have called it subsequent rather than second, because you can have a second and a third and a fourth. So, subsequent roll. Alrighty, first thing we had were those flags. We're going to set them, our starting values. We had 3 of them. We had a target, we had game over, and we had a win. So, win is equal to false. We certainly haven't won right off the bat. Game over is equal to false. Notice that false has to be capitalized. And our target roll, we don't even have a target roll yet, so I'm just going to give it the value of 0. And we're going to need a roll dice function. Maybe we'll put that on at the end, but we have to define it actually up here at the top. We'll come back and add that. Alrighty, so let's get our roll. Total is equal to roll dice. That's the function we're going to have to write. The first version of it we're just going to type in numbers, and then we'll modify it to generate random numbers. So if total is equal to 7 or total is equal to 11, having to use 2 equal signs, then we set our game over flag to true.
What is the true again?
It's a state. Just like, are you done yet? Are you finished? Are you full? Yes, true, I am full. You could write a loop that said, are you full? And while you were not full, when you finally set that flag to true, then you would stop, eating. So it's called a Boolean variable. A Boolean value is either a true or false. It's a very specific range, of only true or false. And so you put it in there so that later on you can either use it on an if statement or we can use it on a while loop. Later on we can do if when is equal to true, and we'll know, that it was set to true at a certain point.
We haven't created what true is yet? We
don't have to. It's orange. It's built into the language.
Okay.
It's one of the key words of the language. It's just a value like, in old programming languages, they treated false as 0 and true as 1, but then they changed it so that the 0 actually had the word false to mean it's not true, and they changed it so that 1 actually was defined as true so that it was true. I think I botched that explanation. But it's so that, here's how people used to do it. They would say or they would do game over is equal to 0. While game over is equal to 0, keep playing. And then something would set game over equal to 1 to cause it to break that loop. It's the same idea, except we're putting game over is equal to false. While game over is equal to false, keep going, and then finally set it equal to true to break out of the loop.
Okay.
And if they happen to roll 7-11 right off the bat, we're going to say you won on the first roll. Else, if we didn't win on the first roll, the number that they rolled becomes our target. So target is equal to total. That will be what we're trying to roll later on in the game. let's explain that to the user, though. If they didn't win on the first roll, now they actually have to roll that as their... So we're going to tell them what they need to try to roll. So underneath that, let's stick our print statement. You need to roll this number again to win, colon, and then that target. Kind of badly worded, but that'll work. So now we have our while loop. We're going to let them keep rolling over and over until they hit that target, or until they hit the dreaded 7-11. While game over is equal to false, we need to roll the dice again. I'm going to scroll this up so that the people... There we go. Now we need to see if we've hit the target. If the roll is equal to the target, great. Game over is equal to true. Win is equal to true. ELIF, which stands for else if. Else if the total is equal to 7 or the total is equal to 11. Game over is equal to true. But did we win? No. So win is equal to false. And then now we're going to backspace so that we're no longer indenting at all. By the time we get here, they've either met one of these two conditions. The roll is equal to target, or they rolled a 7-11. So since game over is now equal to true, it exits the while loop, and we can check to see whether they won or lost. If win is equal to true, colon, print. Great. You're the dice lord. Just kidding. You win. Else, print. Sorry you lost. Try again. Alright. I'm sure I have syntax errors. Let's see. I'm going to save this as June 27 dice. Get it out of the Python directory. It's not going to work because we haven't defined this function. Roll dice is not part of the Python language. We have to write that function ourselves. And since I still hear people typing, I'm not going to scroll up and add it yet. So now that I think of it, I should have added it before. All right, this function needs to be called from within the code. We have to define it before it gets called in this code. So we're going to have to go back up and put it at the top of the program right below our comments. So, and I'm sorry if you're not done with typing this. I can print out the code or whatever in a moment. Up here, underneath that our comments here, we need to define a function called roll dice. It doesn't take any parameters, so there's not going to be anything between the parentheses. It does have a colon there. And this function is going to be a really easy version of it. It's not going to actually do the dice. It's just going to ask the user for what they rolled. Roll is equal to input. Tell me what you roll. That's a real trusting casino that lets you tell them what you rolled. Then we need to convert it to an integer. Roll is equal to int roll. Then we need to return that value so it can be used. So those 3 lines of code, well, 4 counting the define statement, need to go up at the top of the program, right below the comment block. All right, there's all the code on one screen except the print statements are too long to fit. Let's actually see if it works. Tell me what you roll. Well, let's just see if rolling a 7 works. It says great, you won on the first roll. Let's do that again. Tell me what you rolled. 11. That also wins. Okay. Now we're going to test it without getting a 7 or 11 on the first roll. Let's say we roll a 2. Now, you need to roll this number again to win. 2. Tell me what you roll. I rolled a 3. Boom, it blows up. I think I mixed my words up between roll and target. Right here, under subsequent rolls, I say total is equal to roll lies, but then I say roll is equal to target, not total is equal to target. Change that word right there from roll to total. These can't be all the rules. Aren't snake eyes some kind of important role, and boxcar some important kind of role? I don't know. But anyways, we'll go with these rules. Alright, it would be a lot more fun if it was randomly generating the number, but it seems to work. There's our code. Let me wander around and see. So I'm going to do a little bit of googling there. Doctor's one?
But that is how you would add in any other digits.
Right, right. If you were going to make it fail on a 2 or a 12 or to win on, yeah, you would do or total is equal to 2 or total is equal to 12. Got it going? Good deal? Cool deal. Okay, so a couple things would make this program more fun. One would be if the dice rolls were random. Another would be as if it looped over and over and overs, so that you didn't have to run it each time you wanted to play it again. And the third might be for your professor to remember the rolls about 2s or 12s. Box, cars, craps, rules. Let's do that. I'll probably mess the rules completely up. Okay, if you roll a 7 or 11 to begin with, you win instantly, but if you roll a 2, 3, or a 12 at the beginning, you lose.
3, 2.
Yeah, apparently this is pretty rigorous. Alrighty. Yep, I did have the rules wrong. I think it won't take much to modify them though. For one thing, we need to, if you roll at an 11 during that repeat cycle, that wash, rinse, repeat cycle, that does not cause the game to end. So in the subsequent roll loop where it says L if total equals 7 or total equals 11, remove that or total is equal to 11. That is incorrect. So from our original code, we had to change that line, and now we also had to just change this line. And I removed the colon. I need to put the colon back. There we go. Secondly, is if you roll a 2, 3, or 12 right off the bat, that is also a fail condition. So we need to modify our first roll logic. Here where it says if total is equal to 7 or total is equal to 11, game over is equal to true, win is equal to true, print you won on the first roll. We're going to add the rolls 2, 3, or 12 to that. So above that else statement, we're in the first roll section now. Above that else statement, do elif total equals 2 or total equals 3 or total equals 12, colon. Game over is equal to false. No, game over is equal to true. Win is equal to false. Print, you lost in the first roll. All right, and the betting rules are more complex than I want to try to implement. But the dice rolling, that's about right. So, anybody getting any weirdness when they're running it at this point? If it's good, yours? Okay. Okay. Last thing we want to do is to make it to where we generate a random number, just like in our guessing game from a few classes back. So to get the random number generator to work, above the DEF statement, we need to add an import. Make it say from random import RANDINT, random integer. So now let's just make it to where they have to hit enter to roll again. So let's change that message, instead of tell me what you roll, to hit enter to roll again, or hit return, yeah, enter to roll again. And then our roll is going to be the random number that we generate. RANDINT, okay. Now just generating a random number between 2 and 12 isn't accurate. You actually have to generate 2 random dice and then add them together. And the reason for that is we want to approximate a bell curve rather than a linear distribution. Well, I'll show you what that means in just a moment. So we're going to say, we're going to delete that line that says roll is equal to input, because we're not storing anything after they hit enter. But we're going to do roll1 is equal to RANDINT between 1 and 6. And then roll2 is equal to RANDINT between 1 and 6. And then a roll is equal to roll1 plus roll2. So we roll our 2 dice, we add them together, and we return that. If we're trying to turn ourselves into big shot gamblers, we would need to learn the terminology. The first roll is called coming out. I just read that on Wikipedia, so I am smart. And then that target is actually called the point. And rolling a 7 in order to win or to lose. Anyways, I've already forgotten what I read. Let's give that a shot. Hit enter to roll again. You need this number again to, okay, it's not telling me what I rolled. That's kind of a drag. Why don't we, after we roll the number, print it out? So above that return statement, print, you roll a, comma, or maybe you just rolled without the A, and then the total, roll. There we go. I don't like the word again, because it says it even on the first try. So, yeah, I'm going to take that word out, and then I'll be happy with the program. Now, one thing we could do is just to make the game run over and over endlessly to find out your probability of winning this game or losing this game. I think it turns out you win like 55% of the time and lose 45% of the time. All right. What are the lessons learned here? Well, one is I wanted you to see the OR statement. Notice that OR is lit up. It's actually part of the vocabulary. There's another key word called and. And they work pretty much the way they do in the English language. If total is equal to 7 or total is equal to 11, then ta-da, we've won. But if it's and, then both sides have to be true before you go in there. Like if it said if total equals 7 and total equals 11, this would never be true, right? Because you can't have that same number being both equal to 7 and 11. So OR and are known as Boolean operators. We already have our operators, our plus signs and our minus and our times and stuff like that. But now we have Boolean operators. Meaning that they work on logical values. Normal operators, work on digits, normal math, base 10 or whatever. So the way they work is like, say you said x is equal to true. Or no, let's use the examples from the game. Let's say that we said if game over equals true and win is equal to true, we could print, don't put this in your code, you win. If game over is equal to true and win is equal to false, then we print you lose. If game over is equal to false and the number of times we've rolled, let's call it attempts, we didn't actually put that into the program, is greater than 100, well, let's print, let's give up. That's the way you use the AND or the OR operator. You stick them between two conditions that will evaluate to true or false. Whenever you see equals true, you could shorten the expression by removing that equal true. We could go back in our code. You don't have to do this, but you could. Everywhere it says equals true, which I think is just down here at the bottom, you could delete that part. So where it says if when is equal to true, you could just do that. If when. Because when equals true evaluates to either true or false, but when is already either true or false. I think that's the only place we do that. Up here we do equal false. You can replace that by deleting that part and then putting the word not in front of it. I could take that out and put while not game over. While not game over is the same thing as while game over equals false. And if when is the same as if when is equal to true. Put those in our notes. I don't mind putting the equal false and the equal true, because I think Vernon asked, what is this true business and this false business? If we don't put that in there the first time we see them, then it's more confusing, in my opinion. Okay, so I'm going to leave them like that, but I'm going to go put some comments over here in our notes. You can replace equal true. Replace isn't the right word, is it? You can delete equal true from your code, and the comparisons will still work. So if you have if game over equal true colon, this is the same just as if game over. You can modify or you can delete equal false by using the not keyword. So if when is equal to false, this is the same as saying if not when. So these are known as Boolean expressions, Boolean evaluations, because they return a true or a false. We've done math expressions already, like a is equal to 2 plus 7. Well, that 2 plus 7 is an expression that evaluates to 9. Well, when equals false, that evaluates to a true or false. Total is equal to 7. That evaluates to true or false. It is a Boolean expression. George Boole was a mathematician who created the idea of a math that existed in a universe where there were only two values, 0 and 1. And he came up with some specific rules about that. I'm going to babble about them a little bit, but that doesn't mean that I want you to, you don't have to commit this to memory, but then we will commit it, a little bit of it to memory. That will be very specific about what I want you to remember. So Boolean math, invented by George Boole, is math where there are only two values, 0 and 1, which we could call false and true. And the operators are this. Instead, you have addition and you have multiplication. 0 plus 0 is equal to 0. 0 plus 1 is equal to 1. 1 plus 0 is equal to 1. 1 plus 1, well, it's not equal to 0, is it? But in this universe, we only have two numbers, 0 and 1. So there we go. So that's the addition operator. And we are coming up on something I'm going to be a jerk and make you remember. So when I say that, your eyes will want to flicker up to the screen. Then there's multiplication. 0 times 0. 0 times 1. 1 times 0. 1 times 1. Okay, what is 0 times 0 in our math or any other? Yeah. What's 0 times 1? Yep. What's 1 times 0? And lastly, what's 1 times 1? Okay. So those are two Boolean operators expressed as math symbols. If we wanted to change these into computer Boolean with true and false, we would change the pluses into ors, and we would change the times multiplication into ands. And I'll show you what I mean. I'm going to take this one and do 0 or 0 is equal to 0. 0 or 1 is equal to 1. 1 or 0 is equal to 0. Excuse me, 1, and 1 or 1 is equal to 1. There we go. What does that mean? When you use or, only one side or the other has to be true. Like, what are the conditions that I'm going to use to decide whether I'm going to eat out? Or whether I'm going, nah, not going to do that one. I want to use an or. How am I going to decide whether I am going to stay home? If I'm sick or I am tired. If neither one of those states is true, I'm going to stay home. If sick is 0 and tired is equal to 0, I'm going to stay home. But if sick is 0 but I am in fact tired, I am going to stay home. I think I worded that wrong. It looks better if these are expressed as trues and falses. So now I'm going to take the same thing and replace the zeros with false and the ones with true. This actually is really darn important. I'll wind up putting it again, but you just need to remember that when you're using an or, if either expression is true, the result is true. Otherwise, the only time the expression is not true is if both inputs are false. And so our logic will be, if sick and tired, these are our two variables. If sick or tired, yeah, stay home and watch Netflix. There we go. So, if sick is true, we're going to stay home and watch Netflix. If sick is false, well, that's all right. We're kind of lazy. If tired is true, we're going to stay home and watch Netflix. Actually, if we're tired, we're going to probably sleep through Netflix, but whatever. And if they're both true, well, we'll still stay home and watch Netflix. So that's an or statement, broken down mathematically rather than just worded as, in English, or means either one or the other. This is it broken down mathematically, because they're treating or as Boolean addition, and in Boolean addition, 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, and 1 plus 1 is equal to 1. So, false or false is false. The rest of them are true. False or true is true. True or false is true. True or true is true. That may be actually harder to remember than just, if one side or the other is true, then the result is true. However you want to burn it into your brain. If we put this in the form of a table, 3 columns, like this, that's called a truth table. So we're going to say that this is X, this is Y, and this is X or Y. Turn it into a hunky-dory pretty table and we'll be done. I said a pretty table. There we go. That's a truth table. That's the or truth table. Be able to write that. I should give you a pop quiz right dang now, except I think people have already started going to the bathroom. We'll take a break as soon as we do the and truth table. So the and works the same way, except we're replacing the multiplications with the word and we're still replacing so addition is the same as a Boolean as or in computer logic. All of that is about that. Multiplication is the same as and in computer logic. So we're going to say 0 and 0 is 0, 0 and 1 is 0, 1 and 0 is 0, and 1 and 1 is 0. Now let's replace the zeros with falses and the ones with trues. So false and false is equal to false. False and true is equal to false. True and false is equal to false. The only one that's true is that one. So our and truth table, notice that the only time or is false is when both inputs are false. The only time and is true is when both inputs are true. So let's change this to X and Y. All of these results are going to be false except for the last one when both X and Y are true. And so an example of that is we're going to decide whether we're going to eat out or not. What are the two conditions that have to be true before it's fun to go eat out? One is we have to have money, And 2 is we have to be hungry. If we don't have money, we can't go eat out. If we're not hungry, there's no point. So have money is one Boolean variable, and are hungry is the other Boolean variable. So if have money and are hungry, let's eat out. Both of these have to be true. If we have money but we're not hungry, there's no point to it. So that's if true and false. So we won't execute the if statement. If we're hungry but we don't have money, I have those reversed, but you get the idea. The only time we eat out is if these are both true. So when you're using and, only one of these 4 conditions will actually allow us to execute the if statement. You can mix and match those in a sentence, in a statement, and the logic becomes kind of harder to follow. If have money and are hungry, or sick and tired, or, whatever. You can mix the and ors. We'll talk about the rules for doing that after our break. Let's take a 5-minute break. Be back at 1:45, y'all. Good idea. Remind me to start it again. All right, so the last Boolean operator is not. And I'm also going to show you the symbol for these in other languages, like C, C++, C#, and Java, which all use a symbol, a keyboard symbol, rather than, pardon me?
Did you set the recording?
I did. Thank you so much. Brownie point for Andrew. Okay. So the last one is not. Not just reverses it. Like if you do this one. If hungry is equal to false, not fails. I always type that. There we go. Not reverses the truthiness, if we're going to use Colbert's old thing about that. So if hungry is equal to false, like I mentioned, could be reworded as if not hungry. So if not hungry, say, no thanks, I'm full. So if hungry is equal to false, we're going to say, no thanks, I'm full. It's the opposite of the other if statement. Earlier we were saying if hungry, if total is equal to something. If temperature was greater than something. So its truth table looks a little bit different. You have X and then you have not X. If X is false, it becomes true. If X is true, it becomes false. So hopefully that's pretty clear. If you have a complex expression, the not just reverses it. So you could say if X is, or if temperature is greater than 32 and the temperature is less than 212. So unless you live in a place like the rest of the world where you use Celsius, that's the boiling point and the freezing point of water. Instead they use, 100 and 0. So if temperature is greater than 32 and temperature is less than 212, we will print water is a liquid. And of course this is not valid Python. If we were going to do valid Python, we'd have to be putting parentheses around there. But you could reverse that logic. You could say if not temperature greater than 32 and temperature less than 212, then print water is not a liquid. So some languages, and I think in math it's written as, well, no, not in math. This is used as or. Those are the two vertical bars above the enter, shift, backslash. This means and that means not. Those are the languages that are derived from C. An awful lot of them do that. So if you ever see and, or even a single and in a programming language, it might mean and, especially if it's in an if statement. And if you ever see two bars in an if statement, you know that it's or. Our language doesn't do that. And then that means not. So if we were going to write this statement, rewrite it using those symbols, we would do this. If temperature is greater than 32, oh, see, I did it right up there without even thinking. And temperature is less than 212. And if you wanted to reverse it, you would do that. Those mean the opposite of each other. This one calculates to see if it's a liquid. This one calculates to see if it's not a liquid. What if you didn't want to use not in order to do this? You could rewrite it so that you didn't use not. And I'm going to go ahead and show that. It's applying a specific mathematical rule that I don't remember the name of, and so I'm not going to ask you to memorize it. We could say if temperature is less than or equal to 32, because that's freezing, right? Or the temperature is greater than or equal to 2012. So now we're using or rather than and. So if it's freezing or it's boiling, we print water is not a liquid. This is mathematically the same right here as that. The logic is exactly the same, but it's worded differently. This one uses a not in front of it and it has parentheses, and it uses and. This one doesn't put not in front of it. It reverses the condition. It's greater than or less than or equal to 32 rather than greater. And it uses an or. And so there's a specific process for doing that. If you want to get rid of a not in front of a long expression like that, you reverse these expressions, make them greater than if they were less than if they were greater than, and you switch the and to an or vice versa. I don't really care about that, but I do want you to realize that there's more than one way of wording these things. And as a programmer, you're better off if you word it in what makes the best sense to you. I like this one a lot better than this one, myself. My brain parses this one better. The or is really easy to parse. There's no not. I'm not having to calculate something and then flip it in my brain. I can understand the logic of this one better than I can this one. So when you're writing your programs and you're mixing up your logic, or you're creating your Boolean expressions, your ands and ors and ifs, then just know that you can make it awfully complicated, but you could also try to simplify it. And this is just more like trivia, but I'm going to go ahead and mention it. If we said A was equal to temperature greater than 32, and we said B is equal to temperature less than 212, let's, instead of single letters, let's do freezing, and let's use boiling as our two things. Then we could reword them like this. If not, freeze and boil, then print water is a liquid, or water is not a liquid. That doesn't look right.
Water isn't that sound?
Yeah,
Water isn't.
right. Water is a liquid. There we go. Or you could say if freeze or boil, print water is not a liquid. What's the difference between doing it this way and this way? Well, you create your variables beforehand and it makes your expressions easier to read. To me, It's easier to read if I have some English-like words here. If not, freeze or boil. If freeze. I think this is wrong.
Wouldn't you want your temperature to be less than 32?
Yeah, yeah. And that one should be greater. And that should be an or. There we go. There, see, I'm messing it up. I think that's about as far as I want to take that. I think that I'm kind of taking that off into La La Land. So if we have rich is equal to money greater than 0, and we have hungry is equal to, I don't know, hours since we ate greater than 2. We get hungry every 2 hours. Then we could do if rich and hungry. And I'm putting parentheses around that, although that's not necessary in Python. It is in some languages. Then we print go eat. Or go out to eat. This is creating flags, creating states, Boolean variables from in order to simplify this expression. We could put if money greater than 0 and hours greater than 2 directly into the if statement, and it would work just as well. If you think that it makes the logic easier to read, you might do it that way. If you don't think that the logic is easier to read, you may as well just do this. If money greater than 0 and hours since we ate greater than 2. No. If that's easier for you to read, write it like that. If it's easier for you to read, it's probably easier for other programmers to read as well. So, you just use your judgment. And you can mix in Python, well, in any of these, you can kind of mix and match them. If money is greater than 0 and not money, and not something else, and not bills due. Then do something. Print. Let's go crazy. And blow it all on popsicles. There we go. Yeah. There we go. Okay. So now we've expressed it like this. Money greater than 0 and not bill due equal to day. We could reword that if we wanted to. I don't think I'm going to bother. But you get the idea. We have a not here, in the middle. Maybe that makes it hard to read. Maybe we want to change this to not equal today. If you do not equal, it's exclamation mark equal sign. Because you could do, if temperature is if not temperature equals 100. Or you could do if temperature not equal to 100. Both of those are valid statements. It's just that this is a little abbreviation. All right, let's go back to how to think like a computer scientist. I don't know if the dice game is more fun or less fun than Turtles. I think it's less fun. The other concept that was important from what we just did is the idea of the function. We defined a function called roll dice. We made the program modular. You could call that a module. We don't really call them modules in this language. But, you know, we're kind of used to the idea of the term module because we heard the term modular. It's where you take something and you encapsulate all the logic necessary to do that particular thing in one little block of code. You give that block of code a name. If it takes any extra data that you have to pass in, you put those between the parentheses, and then you put some statements. And if it needs to return a value, like our roll the dice program did, then you put a return statement at the bottom of it. And by making it modular, you know, in our program, we could have done this. In the dice game, instead of saying roll dice, I could have put all that code right there. I could have done this. I'm going to comment that out. And I could say input, hit enter to roll. I'm making, and then I'd say roll 1 is equal to random int, blah, blah, blah. You know, roll 2 is equal to random int, blah, blah, blah. And then the total is equal to roll 1 plus roll 2, and then we could print the total. You rolled a, you know, total. There we go. We could put that every single time we wanted to roll the dice. So I could copy that code, and then I could come down here, and then when we need to roll it again, during our while loop, I could paste that code. There. Now that code is in the program twice. What if we wanted to change this so that we were weird and use D&D dice and we wanted to roll 20-siders? We'd have to change that in more than one place. We'd have to find where we pasted that code here and where we pasted that code here. By making that a module, by making that a function, rather than embedding all those statements more than once, we made it easy to change. If we wanted to change the rules of our game so that we rolled 2 20-sider dice, we could do that in one place. And do you remember how with the first time I ran it, it didn't tell me what it rolled? I was able to make it display that message everywhere I did it just by changing it in one place, by changing it in the function. So that's why you make things modular. They're easy to debug. They make the program, you know, the code down here smaller and more concise and hopefully more understandable. And by putting all the functions involved in dice rolling in one place, it's easier to change. What if I had done that stuff where I did the tell me what you rolled, and then later on I wanted to replace that with random numbers? If they were not written as functions, I'd have to go all the way through the code and find everywhere I rolled the dice. Now in this case, you know, it's only twice. It's not a big deal. But what if our game required lots of calls to the roll the dice function? You know, you're playing Yahtzee and there's all sorts of times when you need to roll and you need to not roll or whatever. You know, it could be that this function is called 100 times or 1,000 times in the program. And so by encapsulating it all in one function, so that you can just invoke that function, then if you need to change the behavior of it, you can do so. Another example might be calculating a tax rate or something. You could calculate the tax rate, you know, down here in your code. Maybe it's hard-coded and you put, you know, the tax rate as being 8.25% or whatever it is in Midwest City, and you paste that number in 100 times in your program. Or you write a function called getTaxRate, and it returns 8.25. Well, when the tax rate changes, you only have to change it in one place. So by putting stuff in functions, you're making the code more modular. You're making it easier to maintain, easier to understand. Imagine what our flowchart would look like if I had not put, where's my drawing? If I had not put my rolling dice function in its own function. I'd have to put 5 different blocks here, you know? I'd have to put the roll the first dice, the roll the second dice, the add the 2 dice together, the press any key to continue, and the print message, you know, saying what you rolled. My flowchart would be that much longer because I'd have to put 5 different statements, 5 different blocks here, and I'd have to put 5 different blocks here. Now the last thing I need to do before I close this, these rules aren't totally right, you know, it doesn't support the 2 and the 3 and the 12, but I don't care about that. What I do care is that this flowchart is not complete until I also add the code for the total, for the roll dice function. So here's how I'm going to do that. I think I'll just scroll down here, find some place to put it. I have to give it a function name. Well, the function name is roll dice. So I could call it roll dice function, or if I want to make it look like Python, I could type def colon, or def roll dice. I'm going to go ahead and make it. No, I'm going to leave it. I'm conflicted. I'll leave it like this. Roll dice function. So rather than start with the word, rather than begin the thing with the word start in the pillbox, I'm going to say that this is a function. And what did it do? What it did is it displayed a message, hit enter to roll, and then it called the random function twice, and then it added those together and it returned it. So I'm going to put, and then it printed it before returning. So it was actually 5 statements long. So print, hit enter to continue. And then this is math. It's actually calling another function. Now we could say, we could put it in the one with the bars because it's calling a function, but it's a function that Python is giving us, so I'm not going to do that. In our flowcharts, the only time we use the statement with the bars down the side is if we're calling a function that we've written ourselves. So this will be roll1 is equal to random int between 1 and 6. And I'm just going to copy and paste that, so I'm going to highlight it, hit Control-C, and then Control-V is in vehicle. Why that means paste, I don't know. It's just because it's near the bottom of the keyboard. And that's roll2. And perhaps I could have put all 3 of these into one block, one math statement. And then total is equal to roll1 plus roll2. Then I need to display the total. So I'm going to need another input-output box. Print your total, or your roll is, comma, total. And then I need to return that value. So when I put this stop pill shape, instead of just saying stop, it's going to say return total. I should hook all these up with lines. I'm going to cheat and draw a line from the top one all the way down to the bottom one. And then right click on that line and do send to back. There. Save myself 5 minutes of trying to get those lines to hook up. Now a lot of y'all add colors to your flowchart already. I'm going to show you one time when I do color code my flowchart as well. And that's for these kind of function calls. Just to make it real obvious how they hook up. If I'm making a flowchart to put in an assignment that has a function, I quite often do it like this. What I do is I pick a color for the definition of the function. Like, I'm going to go to the paint bucket and make that some kind of tan color. And then everywhere I call that function, I also make that the same color. So I'm going to go find the box with the bars down the side, the function call, and also make that tan color. And I did it in 2 different places. There's one. There's the other. Okay. That just makes that jump out. That's not so important. It works just illogically, it doesn't change the meaning, but what if I had 5 different functions that I've written? Might be nice to color one of them pink, and one of them blue, and one of, whatever. And it just kind of makes them jump out. However, if the function is completely unimportant, then, there's really no need to call it out like that with a different color. And since some of y'all are coloring all the boxes different colors anyways, then adding a specific color for the function wouldn't matter. So, that's just something I do. So if you see one of my flowcharts and it has these boxes with the bars, and those boxes with the bars are colored, then that means that you'll be able to find the function pretty easily just by eyeballing it, not even without looking at the name. Okay, so this flowchart and the game program, I'm going to want y'all to upload. I will create a Dropbox for that before we're done. I said I was going to lecture from the slides and I haven't already. Functions. Here's how you define a function in Python. You use the DEF keyword. You've seen that now. You give it a function name and you follow that with parentheses, optional parameters. If we had to pass in something into that roll function for it to work, we would define that there. A parameter is just a variable that you put between parentheses that receives data from the calling code. But our roll function doesn't need to receive data from the calling code. But if we were going to write a print function certainly does receive data. So you can be sure that there is some kind of parameter list inside where they define their own print function. And then after that will be one or more statements. The same rules for variables names apply to function names. They can't start with a number. You can't put spaces in them. So here they have a function. Oh, and we use functions in our smiley face. We defined a function called circle, or draw circle. That's another good example. We had two functions. In order to relocate, we lifted our pin, we went to a specific x coordinate, we went to a specific y coordinate, we put the pin back down and we set our direction up. And we did that so that every time we finished drawing a circle, we would reset our position and our circles we would know where they were, what direction we were going. Then we wrote another function. It called this function. It called relocate. So you can have nested functions, one function calling another one. You don't want one that calls another one and then have that one call the first one again, because that's kind of a circular thing. You probably don't want that. This function changes the color of the turtle. It begins filling, it draws a circle, and it ends the fill. And notice this one did accept parameters. So did relocate. We had to pass in x and y. Our roll dice one didn't have any parameters. So it was defined like that, with nothing between the parentheses. This one has parameters. It has x and it has y. Otherwise, how would it know what x was? How would it know what y was? So if this thing uses data that is calculated elsewhere in your program, you need to pass them in as parameters. This one we passed in 4 different things, 5 different things. We passed in an x coordinate, a y coordinate, the radius, and the color and the fill color. Now what if we didn't have this code? What if we didn't have this function? We would have to have those 5 lines of code right there for that circle. We would have to repeat those 5 lines of code there, and depending on how many different circles you drew, like 7 circles, it'd be really nasty. And we can do that. I would have to do something like this. X is equal to 200. Y is equal to 0. Radius is equal to 200. And then I would have to put all of that in there. Or maybe I would just put those right there, Okay, so x is 200, y is equal to 0. The radius was 200. And then our colors were black and white. So we could replace all that code with these statements. One statement took these 5 statements in order to execute. But this one's also reliant upon a function. It's reliant upon this relocate function. So I'd have to take that and paste that in there as well. So x was equal to 200, y was equal to 0. Our heading was equal, okay, there we go. So one call to draw circle executed all those things. We made them more modular by let's dedent that. So I'm going to choose format dedent, pops it back like that. Whoopsie. Now that was just one circle. The next circle would look different. I'd have to copy all this code. We're going to lift the pin up and we're going to move to a different place on the screen. We might be going to -100, 50. We might be drawing a circle of a different radius, a smaller circle with a radius of 10. It might have different colors. I hope you can see why doing it the way we did and putting those in functions is a lot better. Because if I had 10 different circles, I'd have 10 different blocks of these. And it's much harder to figure out what they're doing. It's a lot easier just to look at it and to see these calls down here. Even if you don't understand what these things do, you can look at that and figure it out as long as you have the idea that that's an X and that's a Y and that's a radius. I ought to define it, document it somewhere so that you could look up the draw circle function and you can figure out what those 3 values are. Or 5 values are. But fortunately, it's coded well enough that we could, just eyeball it. Documentation is always a good thing, and I skipped that since I was having y'all type it in from what I was doing here. Okay. Are we sold? Do we like functions? Here he's made a function called draw multicolor square, where you pass in t, that's the turtle, and then you pass in a size, and it loops 4 times, drawing different colors. Not totally getting that one. That one doesn't look real cool to me, but it would draw a red line, it would draw a purple line, it would draw a hot pink line, and it would draw a blue line, turning left after each one of those lines. And then he calls it in several different places. Actually, he puts that in a loop. That's kind of cool. I almost want to do that. Functions can call other functions, just like the draw circle function called relocate. Here's our range statement again. Remember our for loops? In ranges, you specify a starting place, an end place, and then a step. But if you just want it to step up by 1, you leave the step off. If you want it to start at 0, you leave the starting number off. So what numbers will I equal as it's doing this? The first time through the loop, I will equal what? Well, there's only one number here, so that means that the starting point was left off. I starts at 0. Then the second time, well, there's no step, so it's increasing by time. The second time, I will be 1. And then will I hit 2? The answer is no, because when you're doing a range statement, it starts from 0, but it keeps going, and it stops before it hits that one. Whenever that one becomes true, it stops doing it. And we can prove that to ourselves. Pop open another little idle program. For I in range 2, print I. Now let's run it. I'm just going to call this junk because I'm not going to save it, upload it, anything. There we go. It printed a 0 and a 1. Now if I wanted to specify both the lower number and the upper number, I could do that. So I'm just going to copy those 2 lines of code, paste them. I wanted to start at 8, and I wanted to count up to 18. Now if I wanted to count up to 18, I actually have to make that 19. So I'll put a comment here. This counts 0 and 1. This counts 8, 9, 10, etc. up to 18. If I put a step in there, if I add the third parameter to the range function, then it counts up by the step. So this will count 8, 10, 12, 14, 16, and 18. Don't be so lazy. Let's make that say 11, 12, 13, 14. Now I wish I hadn't gone up to 18. 16, 17, 18. Okay. You have the idea of the for loop. I think we did a for loop that added up all the numbers between one value and another. let's make a list and check it twice. January, February, March, April. And then let's do for month in X, colon, print month. That will print January, February, March, and April. Steps through those. We haven't really talked about lists much yet, but the author of this Think Like a Computer Scientist text seems to feel happy using them before we've actually defined what they are, so I'm doing the same. So when I ran it, it just print January, February, March, and April. And we did that with like Trump and Clinton and Vladimir. So the flow of execution. The flow of execution is the order in which statements are run. In our DICE program, we had a DEF, roll dice. Well, let's skip that, just because it's defining a function. It doesn't actually execute those lines. Define them. May as well actually bring up the code, eh? Why do I keep adding A? I'm not Canadian. Here we go. So, when it's running, here's the flow of execution. This is a command. It actually does that. This is a definition of a function. We're defining the function, but we're not actually doing any of those lines. The first unindented line, or down here, that's where we actually start. So we do that, we do that, we do that. We do that, we do that, and then we call the roll dice function. Now I've changed this code too much. I need to undo that. Delete all that stuff. Okay. Then, when we hit this, it rolls up here. It goes up here and it executes 1, 2, 3, 4. It runs those statements. And it returns that total. Notice this variable name is different than this variable name. Here we return something called roll, and we stored the value of it in total. Is that an error? No, not at all. This one could be called Fred, and this one could be called Wilma, This one could be called Iron Man, and this one could be called Cat. It doesn't really matter. The variable names are just for us to understand. What this is doing is it's creating a number, and it's returning that number, and we need to store that number in a variable. So that's what the statement does. And the flow of execution is it skips the definition, it runs that, it runs that, it runs that. It has to execute the function, it runs all those lines of those functions, it returns back to here. And then it does some more stuff. And we saw the same thing in our flow chart. We execute a statement, we execute a statement, we execute a statement, and then we call a function. It runs down there, it runs those lines in the function. After the return statement, it comes back up here, stores that result in total, and then it executes the next thing. If you have a for loop, then the flow of execution continues to loop until that is done. Man, that looks so bad. I'll leave it as it was. So in our loop, the flow of execution is after it does all that first dice business. If or while game over is equal to false, it executes all this statement, and then it comes back up here and it checks. Does this condition still hold? Is game over still equal to false? If it is, it runs through all that again. And then it runs through it again. That's what flow of execution is. It's like an ant running down your program, and it's jumping over function definitions, and it's just following, the paths. When it gets here, it magically teleports into the function. It runs the line of code into the function. It comes back here. Then we enter our loop. It teleports out of that function call down here, and that runs through the stuff in the function and comes back with the answer. And then it keeps following the maze until we're finally done. When game over is no longer equal to false, it goes down there and it prints, whether we won or lost. Some functions require arguments. Our draw circle needed an X and a Y. If you need to do that, then you pass the values in between parentheses. And the function has to be written to accept arguments. when you're calling them, when you're calling the function, they're called arguments. Inside the function, when you define it, they're called parameters. So they have those different names, but it's not really a big, I don't consider it super important. Sometimes I'll mess up and I'll call these parameters when you're calling them because the definitions are so similar. So in my circle, my smiley program, that's a parameter. That's a parameter definition. A parameter is just a fancy name for a variable that's passed in. That's a parameter there, that's a parameter there. But when we invoke it, that's an argument right there. This argument fills the x parameter. This argument fills the y parameter. This argument fills the radius. You know, x, y, and radius. This argument fills the color parameter. This argument fills that parameter. So, a function is a block of code with a name and an optional parameter list. In Python, it starts with a def with the def keyword. It may have a return statement that returns a value. Our draw circle program did not need to return anything. I mean, why do you need to return anything after drawing a circle? So it did not have a return statement. If I go back to draw smiley, draw circle, after we call end fill, there's no return statement. It would not be wrong to add a return statement there, but there's nothing to return. You know, we haven't calculated a value that's important. So in that case, you can leave that off. Here's a return statement, but it's okay to leave it off. Here's a return statement, it's okay to leave it off. But in our roll dice program, that number is important. We use that number in order to compare it. You know, that's actually our dice roll. So here, we actually have to have that return roll statement, and if we don't, if we deleted that or commented it out, it would break. So let's write a really dummy little function. We're going to write a function that adds two numbers together. Define, add two, it takes two values, x and y. And so the total is equal to x plus y, and then it returns total. No semicolons in this language. There we go. So that's a function. We've written a function that takes two numbers and returns a value. Important. Understand what that's doing. Then later on in our code we could do that. We could print add 2, 10, 20, and it would print 30. Or we could do a is equal to add 2, 1 and 3, print a, and it's going to print 4. There are some built-in functions. POW takes one number and it raises it to another power. Now we already had an exponent function which does the same thing. Right off the bat, I'm not remembering why you would call the POW function rather than just use the exponent operator. And there's another one, ABS, which stands for absolute value. The absolute value is the positive value. So if you pass in a positive number, the answer is positive. If you pass in a negative number, the answer is positive. Then there's one called max. Max prints or returns the largest of the values that you pass in. So like if I do this, and I say, what is the max of 1 and 20? Well, the max of 1 and 20 is 20. What is the max of 2, 40, and 80? It's going to be 80. Now, it's not always the last one, of course. What is the max of 100, 300, 200, 0? 300, because that's the largest. And as you might guess, there's also one called min. The minimum of 100, 300, 200, 0 is going to be what? It's the smallest one. So, max and min and sum and print are examples of built-in functions. built-in functions. Examples. So, max, min, and print are all built-in functions. We don't have to write those functions into our, we don't have to, do a def space max and a def space min. They're just built into the language. Functions can return values. We talked about that. You put a return statement followed by the value that you're returning. Usually it's going to be a variable that you calculated. I think that is enough. All right, let's talk about what's going to be on the exam. Don't stress about the exam. It's open book. Not that we have the books, but we have those online links, for the books. It's open notes. It's open anything that's posted in D2L. I really don't want you to just hit Google and try to find the answer that way. I'd rather you use the material that we've provided. Now, I can't stop you, unless I'm walking around. So I'm trusting y'all to spy on each other. No, I'm kidding. Don't spy on each other. So what is it going to cover? Pretty much anything that we've done as an in-class assignment is fair game. Let's look at what our in-class assignments have been. We know how to write a hello world. We know how to do the binary and the decimal. We know how to do the binary and the hexadecimal. We know some basic Python programming, like how to add, how to write a statement that would add two numbers, or how to write a print statement, how to write an if statement. We really haven't done too much with a for, so if I do a for, it's just going to be a for with a range. Why don't I be typing these in? Okay. Exam topics. Binary, just like our in-class assignment. Binary and hex. No, binary and ASCII. I'll give you the table, just like the in-class assignment. Basic Python, Python. That's half Python, half Bison. Okay. Like print statements. A is equal to 2 plus 3. I'd like you to know the three things that a variable has. I've said them like every class for 4 classes in a row. What are they? They have a name, they have a type, and they have a value. What kind of data types have we talked about so far? We've talked about 4 data types. We've talked about ints, floats, strings, and Boolean. Ints are whole numbers, right? Floats have decimals. Strings are series of characters, held between quotes. What is your name? That's a string. And then a Boolean. How do you convert a string to an int? That's pretty easy, right? You just do this. And you pass the string in. Or to a float. Write 4 lines of code for a turtle called Leo that draws a square. You don't have to put the import up at the top or anything, or the creation of the turtle or the windscreen, just 4 lines of code that draw a turtle. That draw a square or a triangle. How do you draw a square? 90-degree angles. How do you draw a triangle? 120-degree angles. So it could be something like this. If you call your turtle Leo, Leo dot left or right, 90. Leo dot forward, whatever the size of the thing is. Let's make it a 200, and then repeat those things. 4 times. That's a square. Okay, it's more than 4 lines of code. It's 8 lines of code. 8 lines of code that draw a square, or 6 lines of code that draw a triangle. That's how you draw a square. And then a triangle is the same thing, except you turn 120 degrees. And you do that 3 times. Now I am going to actually delete these things because I want you just to have the concept. I'm not going to store them in the notes, so you can just cut and paste them out of there. I see people grabbing for their phones. Just have the idea. You turn a direction, you go a certain distance. Now, how do you remember if it's 90 or 120? Well, you know, a square is made of right angles. It's 90. It has 4 sides. That's pretty easy. A triangle, why is it 120, by the way? Because all of these numbers have to add up to 360. There's 360 degrees in a compass. 90 plus 90 plus 90 plus 90, that's 360, you know. That's 90, that's 90, that's another 90, and then back to normal. A triangle has those 3 numbers. So it's 120. 120 plus 120 plus 120 adds up to 360. That kind of implies how you could calculate how to draw like a 6-sided figure. If you're going to draw a hexagon, each angle would be 360 divided by 6 because it's got 6 sides. Or to draw an octagon, it'd be 360 divided by 8. I'm not going to ask you that. Just all right, if I give you a chunk of code, I'd like for you to be able to draw a flowchart from it. It won't be very complicated. At most, it would have an if statement and a while. You can assume it would have an if statement and a while. But we've drawn several flowcharts that have if statements and whiles now. Know the symbols. What is a math? You know, or a calculation or assignment? It's a rectangle. Let's keep adding these to the notes. Be able to turn code into a flowchart. Won't be complex. It'll have a while loop and an if statement. Know what the symbols mean. What does a square mean as opposed to a diamond? You know, that's a decision block. The squares, I think they call it a process. What is their fancy term for it? Yeah, it's process, okay. And then we call that a calculation or math. Then there's the trapezoid, quadrilateral. What's that used for? Everywhere we've used the tilted square, what did we use it for?
Data.
Yeah, that's the data block. That's either print or out, or, you know, that's input output. That's their name for it, but we will call it input output. Or print, input and print. You know, I would give that correct. But things like that are going to be multiple choice or matching. So they ought to leap out at you. And you know what the start and the stop ovals look like. And then lastly, you know what the function call looks like. That's the predefined process function call. So the square with bars, predefined function call. Or predefined process is what they call it. We call it a function call. They call the ovals terminators, I believe. Diamonds are used for if statements, whiles, and fors. Alrighty, that's really just about it. You're not going to have to write code, but I do want you to be able to draw the flowchart. And you know, I realize that takes a few minutes, so the exam is not going to be super long. Everybody will be able to get it done like probably in 30 minutes, but you know, we'll give ourselves an hour for it. All right, gang, are there any questions?
Are we going to turn that Lucidchart or no?
Yeah, let's turn the guessing game flowchart and source code in.